my pleasure to introduce the first talk this morning by Wienhard, talking about a beautiful world beyond hyperbolic geometry, Anosov representations, and higher Teichmüller spaces.
Thank you very much, and I would like to thank the organizers for having me, inviting me to speak, and I really enjoyed the talk so far. So what I want to do here is, Mark called it yesterday the PR talk for Anosov perpendicular higher Teichmüller theory. It's not really like that, but I want to give you a bit of a glimpse into some phenomena, and I will explain what Anosov representation and higher Teichmüller spaces are. And let me say, in a sense, what I want to do in the nutshell. So I want to recall a few of the things we know well in hyperbolic geometry. So if we look at hyperbolic manifolds and their fundamental groups and look at representations of these fundamental groups in either SON1 or in SO1M, so in bigger actions on bigger hyperbolic spaces. And then I want to show you that actually we see similar phenomena when we look at representations of discrete finitely generated groups, in particular finitely generated hyperbolic or relative hyperbolic group in P groups of higher rank, like SLNR. So when we go to the world from hyperbolic, from the world of negative curvature, when we go to the world of non-positive curvature. With a special focus on Anosov representation, higher Teichmüller spaces, and positivity. So I will explain on that, but I want to start by just going back to hyperbolic geometry in dimension 2. So we have a hyperbolic space where we have different models, and I just want to recall the upper half space model. So we act on the space of complex numbers with positive imaginary part, and SL2R acts by fractional linear transformations. We can extend this action to the boundary. So the boundary is the real line plus infinity, but I want to think of this as RP1. And this action, if we extend it to the boundary, so to RP1, it actually preserves the orientation of this circle. We'll see later why, but I really want to think of SL2R not really as the group of matrices of determinant 1. I rather think of it as the symplectic group, so as 2 by 2 matrices, linear transformations of R2, which preserve a non-degenerate skew-symmetric bilinear form. Okay, so this is our model geometry. So now we are interested in hyperbolic manifolds or hyperbolic surfaces, and I mean, we know on any closed surface of genus at least 2, we can endow it with a hyperbolic metric, and there are many, many, many different ways of choosing a hyperbolic metric. Picking a hyperbolic metric on this surface is the same, essentially, as taking the fundamental group of the surface as embedding it as a discrete subgroup in the group of isometries of the hyperbolic plane. And we have Teichmüller space and modulus space, which in some sense parameterize the hyperbolic metrics on a surface. So Teichmüller space parameterize it together with a marking so that we get a nice ball, a nice vector space, really, a nice smooth manifold. And modulus space, we forget the marking, it just parameterizes hyperbolic structures. And so it's a 4x4, it's a bit more ugly to look at. And one other key point, which I would just like to highlight, even though I'm not going to say much about this, but if we look at Teichmüller space, the marking has this nice feature that you can name curves on the surface, which you cannot do in hyperbolic space. So you can pick your topological model of your surface, you pick a curve, and then in Teichmüller space, you know this is that curve. And in the modulus space, you just know this curve up to the action of the mapping class group, so you lose some information. So the way I want to think of this space of hyperbolic metrics or Teichmüller space is really thinking of it just by looking at the induced representation on the fundamental group of the surface. So if I put a hyperbolic metric on the surface, I can look at the universal cover. It's now a hyperbolic simply connected manifold, so it's the hyperbolic plane, and I can look at the action of the fundamental group on the universal cover, so by isometries on H2. So I really have a representation of this abstract finitely generated group, the surface group, in the isometry group of the hyperbolic plane. And I want to think of hyperbolic structures as these representations. And then a very nice thing happens for PSA2R, that the set of representations I get is actually a nice subset of the set of all representations, namely it's a connected component. And the way these representations come about as holonomy representations of hyperbolic structures, they all give me discrete embeddings. So I really want to focus on this view of Teichmüller space as a connected component of the set of representations of the fundamental group of my surface into PSA2R, which consists entirely of discrete embeddings. Okay, so now I want to take a step back and tell you about something completely different, and then in the slide after tell you what it has to do actually with hyperbolic structures on the surface. So, but now we forget about geometry, we look at more number theory. So there's so I want to introduce you to Markov numbers. So these are special solutions of this Diophantine equation, so this Markov equation, x squared plus y squared plus z squared minus 3xyz, and you look for integer solutions to this equation. And so it was already known to Markov that actually you don't have to be very smart to find all solutions to this equation. You find one solution, and one solution, the first solution what comes to your mind is 1, 1, 1. And then you can reach any other solution by just applying the following move. So if you have a solution x, y, z, you keep y and z, and you change x to y squared plus z squared over x. So you get a new solution. So now you do the same with y and with z, and you continue doing that. So you do this move and you commute, and then you get this Markov tree, which gives you, now if you go along it, all solutions to the Markov equation. So there are a lot of number theoretic questions about Markov numbers, Markov equations. There are some very big open questions still. I'm not going to talk about all of those. I want to talk about what does this have to do with hyperbolic geometry. So this has a relation to hyperbolic structures on a very simple surface on a one-puncture torus. And let's see how we get Markov equation and Markov numbers out of that. So if you have this one-puncture torus, you want to try to parameterize all hyperbolic structures on this one-puncture torus. And to do that, it's useful to choose some combinatorial or topological structure on the surface. So we take this one-puncture torus, we pick an ideal triangulation, so a triangulation with vertices in the puncture. And then we can unfold this torus, so we have this quadrilateral with one diagonal. So now we want to put coordinates, and to put coordinates we use one other thing to help us. Maybe we pick around this puncture a horse cycle. So you just fix it. Doesn't matter which horse cycle, but you fix it. So once you fix the horse cycle, you can do the following thing. So your ideal triangulation is given by arcs, which go from the puncture to the puncture. These, you make them geodesic arcs. These geodesic arcs have infinite length, but if you fix a horse cycle, you can look just at the part of this arc which is outside of your horse cycle, and this has a finite length. So for each arcs which give you the triangulation of your surface, you pick this length, and so you get this numbers A, B, C associated to this quadrilateral. So now what happens if you change your triangulation? So now triangulation is not so nice because, I mean, this was a choice. So we can change the triangulation by flipping the edge. Flipping the edge, and this is a computation in hyperbolic geometry, gives you a new coordinate A prime. And there's this relation that A times A prime is B squared plus C squared. So if I flip the triangulation, I get a new coordinate A prime B C, where A prime is given by B squared plus C squared over A. So what you see is precisely the same move as you see for Markov numbers. So where does the Markov equation come in? So in this whole picture, I mean, the coordinates depend on all the choices we made, but there's one geometric ingredient which does not depend on the coordinates, which is the length of the horse cycle. So we made a choice of the horse cycle, and this has a length in the hyperbolic metric, and no matter how I change my triangulation, this length doesn't change. But I can express this length of the horse cycle in terms of my parameters, and it's expressed by this function f of ABC, so it's 2 times a squared plus b squared plus c squared over ABC. And so now if we start with a equals 1, b equals 1, c equals 1, we get that this length of this horse cycle is 6. And we get, since this doesn't change, if we change the move, we get really back the Markov equation. So you get Markov numbers by looking at hyperbolic structures of one-puncture numbers. Okay, so that was a short interlude, and because I want to come back to that, just see it as one application of hyperbolic structures on surfaces. So now I want to go from hyperbolic geometry in dimension 2, 1 dimension higher, hyperbolic geometry in dimension 3, and just remind you of a couple of things we see there. So, of course, we all know by Thurston geometrization and constructing hyperbolic, I mean, many manifolds, 3-dimensional manifolds carry a hyperbolic structure. We also know that things behave very different. The fundamental groups of closed hyperbolic 3 manifolds behave very differently than surfaces because we have most rigidity, right? If I give you the fundamental group of your hyperbolic 3 manifold, there's a unique hyperbolic structure on your 3 manifold. So we cannot have this continuous deformation space of embeddings of the fundamental group of a hyperbolic 3 manifold in the isometry group of hyperbolic 3 space. But we can have that if we go from hyperbolic manifolds of 1 dimension to hyperbolic manifolds of higher dimension. So let's first look at this in dimension 2. So we have these quasi-Fuchsian groups. So we take the fundamental group of a surface, right? It acts on H2. We think of H2 as being the equator of the disk in the wall. And now we can start. So instead of thinking of this representation in SL2R, we can think of it in SL2C and deform it in SL2C. And when we do that, we get a quasi-Fuchsian representation. So what changes? So the boundary of the equator, which was the limit set of the surface group embedded in H2, so all the accumulation points of my orbit, if I go out to infinity, this changes to the limit set in the sphere at infinity in CP1, and this round circle will become a quasi-circle. So it will be just homeomorphic to a circle, but usually it will be a fractal curve. And I get still some nice geometric structure, because if I remove the circle and I have CP1 minus the circle, I have the upper disk, the lower disk, and I get 2 complex projective structures on the surface. So, and the set of quasi-Fuchsian representation gives me, if I think of it in the character variety, gives me a nice open subset of the character variety. So there is something interesting if I take a surface and I embed it in hyperbolic, isometry group of hyperbolic 3 space and deform it there. There I can do something similar even for not all necessarily, but for 3 manifold groups. I can take the fundamental group of a 3-dimensional manifold. It acts on H3. I embed H3 in H4 or in some bigger Hn. And then if I think of this as an action on this bigger Hn, I can actually deform it. There's one nice geometric feature which is preserved if I, for small deformations of that. Namely, all these small deformations are what are called convex co-compact subgroups. So if I look at this group acting on Hn, or big Hn, it will preserve a convex closed subset on which it acts co-compactly. And so these convex co-compact subgroups are particular nice subgroups of the isometry group of hyperbolic n space. Okay, so let me just give you one other example, which, I mean, this is more, again, example which you want come from more number theoretic constructions. This is the Apollonian circle packing group. So as you can take this sphere packing and think of this as sitting in CP1 or an affine chart in CP1, and then if you take the group generated by reflection in the circle, you get a discrete subgroup of PSL2C. This will not be convex co-compact, but it will just be nice, it will be geometrically finite. So if we summarize this a bit in this landscape of how does the situation look like for discrete subgroups of isomet groups of hyperbolic, isomet groups of hyperbolic spaces or rank 1 Lie groups, we basically have among lattices co-compact and non-co-compact. Then we have this bigger class which contains co-compact lattice of convex co-compact subgroup, and we have an even bigger class of geometrically finite subgroups, and then we have groups which are somehow much wider, which we don't understand. So I want to highlight a couple of points why convex co-compact subgroups are so interesting, or just some of the nice geometric properties they have. So the first is it's a dynamically stable class of discrete subgroups. So if I think of this convex co-compact subgroup as you give me a finitely generated group and I embed it into the isometry group of hyperbolic n space as a discrete subgroup. If this embedding is convex co-compact, then any small deformation will stay convex co-compact. So you can't destroy it by just wiggling the generators of your group. The other important property, geometric property, is all quasi-convex co-compact subgroups are quasi-isometric embeddings, and actually this characterizes convex co-compact subgroups in rank 1. So you could, if you don't like geometry, if you like more distortion in groups, you could think of these groups in the same way as just quasi-isometric embedding of your finitely generated group into the isometric group of hyperbolic n space, where the length, induced length on the orbit is comparable with the length, the word length in your finitely generated. I also gave you this example for quasi-function representation. This holds more generally for convex co-compact subgroups. They give interesting geometric structures on manifolds. There are interesting relations if you want to study the growth of an orbit. So we have this discrete group acting on hyperbolic n space. So you can look at how many orbit points are in balls of radius n, and let n go to radius r, and let r go to infinity. And there are interesting relations between this orbit growth and the Hausdorff dimension of the limit set at infinity. So between, in some sense, counting the asymptotic of growth inside of the space and its behavior at infinity. There's also, and I mean, there won't go into detail at all, but if you look at the Hausdorff dimension, for example, for quasi-function representation, variation of the Hausdorff dimension also gives you back a nice realization of the Weil-Petersen metric, so Riemannian metric on Teichmüller space. So now I want to somehow leave the world of negative curvatures or rank 1 Lie groups and go to Lie groups of higher rank. So where, if we look at the symmetric space associated to this Lie group, we have non-positive curvature. So we really want to consider basically any reductive Lie group, but I mean, if you don't like arbitrary Lie groups, you could focus on SLNR or the symplectic group SP2NR as the group of interest. And whenever we have a discrete group, the discrete group acts, and it actually acts nice, properly discontinuously on the symmetric space associated to G. So on the space G mod K, which is a nice Hadamard manifold of non-positive. I mean, it has non-positive curvature, but a lot of structure. So there are two, I mean, somehow clear separations. First, we can look at lattices, so discrete subgroups which have a finite co-volume, or we can look at discrete subgroups who don't have finite co-volume, so which are not lattices, which means that if we look at the quotient manifold, this locally symmetric space, we have a space of infinite co-volume. And so I'm mostly interested in groups which are not lattices. So here is,
tell us about the picture.
Yeah.
There's a picture.
There's a picture.
Can you tell us about it?
Okay, so this picture is, I can say one word about it. So this picture illustrates somehow the idea of how a symmetric space of higher rank looks like. So you have flat subspaces, and I mean here of dimension 2, and then whenever, and in some sense transversely to that, you have hyperbolic, you have negative curvature, so you have hyperbolic planes or also higher dimensional hyperbolic spaces. So this is a schematic picture. This actually, and this is perhaps interesting because the title of the conference is Non-Positive Curvature and Applications. This comes out of a paper where we use symmetric spaces for representation learning and machine learning tasks, so for graph embeddings, but not necessarily Cayley graphs, but just arbitrary graphs in these spaces.
Does it have anything to do with the technique of bending, which you have along the flat? You seem to take a lattice and bend along the flat, is that?
Yeah, I mean here, no, I mean here we just, I mean this is just, you take a graph which in some, has some parts which look like trees and other which look like grids, and you try to embed it in such a way that the tree-like parts go along hyperbolic subspaces and the grid-like parts go along flats. But there are bending constructions you can do actually along flats.
So I thought it's related to your line there, gamma, an example of a gamma that's not a lattice.
Yeah, it's actually, I mean, this is in some sense, partly what I want to tell you, if I have a discrete subgroup, and we see that for this convex co-compact, right, groups in rank 1, they are quasi-isometric embeddings, so I can think of this as taking the Cayley graph of my group and embedding it, quasi-isometrically, so with little distortion, in a sense. So this picture is in some sense even a bit more general, because you can take an arbitrary graph and try to embed it into the space, minimizing the distortion function. So, but it's it's hard to draw nice pictures of symmetric spaces because of higher rank, because they tend to be higher dimensional. So here's another picture, and this is in some sense the only more precise example I want to give you of such a symmetric space of higher rank is the Siegel upper half space. So this is the symmetric space associated to the symplectic group SP2NR. And this is really nice because you should really think of it as a version of the upper half space, but instead of doing it over the real numbers, you do it over matrices. So adjust the space, now you have not a symmetric 1-by-1 matrix with complex entries, but symmetric n-by-n matrix with complex entries. So that if you look at the imaginary part, this is a positive definite matrix. So n equals 1 is the upper half plane model. The symplectic group, you can write it as block 2-by-2 matrices. It acts by fractional linear transformations. It preserves and extends to the boundary. So the boundary is n-by-n real matrices, union infinity, but infinity now is not one point, but it's a really big point. So there are a lot of things at infinity. And so a better way of thinking about the boundary is by looking at Lagrangian subspace of R to n, which again for n equals 1 is just RP1, right? And this we see a little bit later, the action at infinity also preserves some kind of positive structure. But this is, so you can think of this one example where you can really think of the symmetric space as being like a hyperbolic plane of subsymmetric spaces. So if you draw a geodesic here, what is a geodesic in H2? Here it would be in the, if n equals 2, it would be H2 cross R. So it's like a small tube of hyperbolic spaces. Okay, so here is just one short slide to summarize some of the things, classical things about discrete subgroups of higher rank Lie groups. So we all know if we have lattices, by Margulis' Simon work, they are all, lattices are rigid, they are super rigid, so we have much stronger than rigidity. Any basically unbounded representation of a lattice extends to the Lie group. And every lattice is arithmetic, so everything comes from number theoretic construction. So, of course, lattices are still very interesting, but just from some point of view, you could say we know all about lattices. Of course, we don't. There are many, many interesting questions, but I don't want to focus on lattices. I really want to focus on subgroups which are not lattices. And so there's work of Kleiner, Leib, and Kahn, who proved independently that if you are in a higher rank symmetric space and you try to look for convex co-compact subgroups, so subgroups which preserve a convex set, closed convex set, and act co-compactly on them. If you restrict to Zariski dense subgroups, the only thing you can get is lattices. And if you don't restrict to Zariski dense things, the only thing you can get is product of rank 1 examples, but you don't get anything new in higher rank. So convex co-compact subgroup is the same as co-compact lattice, so it's not an interesting notion in a sense. It doesn't give us more. So now what I want to tell you a bit about is the development of this theory of Anosov representation, which were introduced by François Labourie about 20 years ago. And they give you a really nice class of discrete subgroups, which have all the features of convex co-compact subgroups in rank 1. I don't know, you are in the higher rank setting. And there are plenty of them. So this is Anosov representations is the setting. You can give me any reductive Lie group and any essentially finitely generated hyperbolic group. And there's a nice class of representation. So I don't say any finitely generated hyperbolic group has an Anosov representation, but we know by now many have. And so the point I want for you to remember, this is really the appropriate generalization of convex compactness in higher rank. Then I will now tell you a little bit about Anosov representation, and then there are higher Teichmüller spaces, which is a subset of the set of Anosov representations, which really look like a generalization of Teichmüller space in the setting of higher rank Lie groups. So the group you look at is a fundamental group of a surface, and not an arbitrary hyperbolic group. But there are also some features which I'm not going to tell you much about, but I can, if you want to know more about it, when gamma is not a surface group, but for example, fundamental group of a higher dimensional hyperbolic. But these only exist if you have special families of Lie groups. And so basically now, I want to tell you what are Anosov representations, what are higher Teichmüller spaces, what are these special families of Lie groups, and then in the end come back to this connection with Markov triplets. So what are Anosov representations? So they were, as I said, introduced by François Labourie using a dynamical picture. And this where there was some flow which had Anosov properties, and that's why they call it Anosov representation. But I want to give you a bit more concrete characterization of them as the definition. And what I want you to think about them is that they are a very strong form of quasi-isometric embeddings of your group into your higher rank symmetric space. And so if you want a quasi-isometric embedding, of course you have to know, okay, so I have to pick a metric on my space in which I embed. So I have to pick a metric on this symmetric space, this non-positively curved symmetric space. So now there's a nice feature in higher rank that actually there is a vector valued metric on these spaces. So this means if I give you 2 points in this higher rank symmetric space, the invariant up to isometry between the points is not just a number, it's not the distance, but it's really a vector in a Weyl chamber. And I want to explain this a little bit for SLN. So for SLN, you have SLNR, you have the space of diagonal matrices in SLNR, which is the space of, this is a commutative subgroup. And this gives rise to Euclidean subspaces of your symmetric space. And if you look at the tangent space, they're given by the Lie algebra of the diagonal matrices. So now you have diagonal matrices of trace 0, so this is this A. And there's a structure on this subspace given by the root system, because, if you take these, if you take these entries lambda 1 to lambda n, you can order them by size, or you can permute them. And so what is the vector value distance function between your base point and your element of SLNR applied to the base point? You take your matrix in SLNR, and you take log of its singular values. So this will give you lambda 1 to lambda n, and you want to
log of what?
Log of the singular values. So of the singular values. So of the eigenvalues of G transpose G. So G is an n by n matrix. I make it symmetric by taking G transpose G. Now I have a symmetric matrix that has eigenvalues. I take the eigenvalues of this matrix, their product is 1 because the product is the determinant. I take their log, so their sum is 0. So this is what gives me this vector value distance between a base point and an element G applied to the base point. So this is in some sense the metric, but now I want to make this vector valued metric into a number. And now I do something which doesn't give me a metric, but it gives me something very useful. So my metric takes values in this vector space, and now I can apply a linear form on this vector space to make a number. And so there are some particularly nice linear forms given by the simple roots of the Lie algebra, so which are taking the consecutive difference of consecutive eigenvalues, lambda I minus lambda I plus 1. Okay, so this now allows me, if you give me an element of G, it gives you a vector, this vector of singular values, and then I choose a linear form. I choose some alpha I, some simple root, and then it gives you a number, namely the gap of the eigenvalue gap between the ith and the ith plus 1, or singular value gap between the ith and the ith plus 1. Okay, so this is now what we use as replacement of metric in some sense, and then the definition of Anosov representation is just you have a representation of your finitely generated group into your Lie group, SLNR, which is a quasi-isometric embedding with respect to this kind of metric. It's not a metric, but it's some length function. So so this depends on a simple root. One, that there exist constants, that if I take the simple root of this vector value distance function between the base point and gamma times the base point, this is bigger or equal than a constant times the word length of gamma minus a constant.
The eigenvalues is well defined as a set, not as an ordered set. How can you take?
No, it's well defined. I mean, I can order them by modulus. Right? I just take the biggest. I decide to order it by modulus. Yes. And then I look at. I mean, in some sense, I mean, this is well defined up to things which are equal, and then I look at the gap. Right? Okay, so this is what it is. So it's really it looks a bit like a quasi-isometric embedding, but since applying this linear form is not a metric, it has a big kernel. It gives you more information about your embedding of the group, because it tells you if you take a sequence in gamma going out to infinity, and you look at this sequence of singular values you get, right? They go off the kernel of this linear map in a linear fashion. So you have somehow linear control of the gap in the ith singular value if it's alpha I, Anosov. And what this does give you, for example, is that you get, if you have an Anosov representation, you get maps from the boundary of your group into some flag varieties for SLN. So you get the map, if it's alpha I Anosov, you get the map into the Grassmannian of I planes in Rn, and into n minus I planes in Rn. And these are equivariant continuous maps, which have a very strong form of injectivity. So they're not just injective, but if I take a point x and a point y in the boundary of gamma, then the ith subspace of x and the n minus ith subspace of y are in general position. So it's about much stronger thing than just having an injective map. So it's some kind of transversality. So when you do this, and we just do in the rank 1 situation, so for example, for PSI to C, there's just one simple root, and it basically just gives you the length of your vector, so it gives you the metric. So you get just quasi-isometric embeddings, and you just, any Anosov representation is the same as a convex co-compact representation, or as a quasi-isometric embedding of your group. So, but in higher rank you get other things. So in particular, these images of Anosov representations are in general not convex co-compact, because now we have a hyperbolic group and a non-positively curved symmetric space, so you're not going to get a co-compact lattice. And here are some examples. So I want to give you, so the first simple case you can do is you take your favorite example of a convex co-compact representation of your group in rank 1. In rank 1 Lie group. Now you take a rank 1 Lie group, you embed it in some big SLN, And so pick some big linear representation. The composition will be Anosov, and any small deformation of it will also be Anosov. Second example is, in some sense, a class of groups which were studied much earlier by, first by Goldman in this case of SL3R, and then more generally by Yves Benoit in the case of SLNR. These are groups which preserve a convex, strictly convex subset in RP n-1 and act co-compactly on them. So these are also give you examples of Anosov representations. There are two examples which play a role for these higher Teichmüller spaces. So one, Hitchin representation. So for this, you take a representation of your surface group into SL2R. You embed SL2R into SLNR via the irreducible representation. And then, and this is resolved by Goldman and Choi in SL3, and then Labrie for Goncharov in general. Any deformation will actually stay a discrete embedding, so you will get a connected component consisting of discrete embeddings. This is called the Hitchin component, and all of them will be Anosov, actually with respect to any simple root you pick. There are representations of maximal Toledo number, which are Anosov with respect to a special simple root you pick, and also give you connected components of representation. And then in 5, there are a lot of more examples. Now, for example, cubulated groups admit Anosov representations. They are examples of groups which do not admit an embedding into rank, discrete embedding into rank 1 Lie group, but admit Anosov representation into higher rank. So it really opens not just convex co-compact subgroups of rank 1 root, but there are many more hyperbolic groups which now appear as this Anosov representation in higher rank. Okay. So here I want to highlight just in some sense, mirroring what I told you about convex co-compact subgroups, what are the nice geometric properties or dynamical properties of Anosov representation. So first, any Anosov representation is discrete and faithful, so it really gives you a discrete subgroup of your Lie group, which is, has the same type as isomorphic to the finitely generated group you started with. This group acts now, as any discrete subgroup, isometry is on the symmetric space, but you have this, if you're not in the rank 1 situation, it's always action which has infinite co-volume. The orbit map is a quasi-isometric embedding. You have dynamic stability. So also for Anosov representation, it gives you an open subset of the space of all representations. So if you give me one representation, and you wiggle the generators a bit to get another representation nearby. If the first one was Anosov, the second one is also Anosov. In particular, it's discrete and faithful. So usually, discrete and faithful is not an open set of the representation variety. So it's not preserved under small deformations. And there's a nice dynamical point of view that you can view any Anosov representation as a reparametrization of the geodesic flow on your hyperbolic group. So I'm not going to go into detail there. So now what I want to do is just give you a couple of, in a couple of slides, just highlight with some pictures some of the other geometric properties or things we know about Anosov representations. So the first is Anosov representations actually also give you nice geometric structures on manifolds. But now the manifold, because your higher rank symmetric space or your higher rank Lie group acts on only higher dimensional homogeneous spaces, this manifold will not be related to the, for example, if you start with fundamental group of a hyperbolic manifold, you take an Anosov representation, the manifold you get will not be related to this hyperbolic, will not be this hyperbolic manifold, it will be higher dimensional. But in many cases, you get geometric structures on some bundles, compact fiber bundles over your hyperbolic manifold. And the way you do this is by constructing, that's similar to what you do for quasi-Fuchsian representation when you remove the limit set and get a nice action on the complement of the limit set. You do constructions of domains of discontinuities in flag varieties to construct this geometric structures, there are plenty of things you can play around with. So one thing I particularly like is, I mean, you can also play around with these domains of discontinuity and these geometric structures to actually give very explicit compactifications of this infinite volume locally symmetric spaces you get. So the other thing I mentioned for convex co-compact subgroups is there's a relation between orbit growth and Hausdorff dimension, and there's some interesting things about Hausdorff dimension. I want to just highlight here one thing which is different in this higher rank situation, and again adds new phenomena you don't see in the rank 1 and the negative curvature relation. So in hyperbolic geometry, we basically know, and I mean it's for surface groups it's made explicit by the theorem of Bowen, that the limit curve is either smooth or fractal. So if I start with, if I have a quasi-Fuchsian representation of a surface group, either it preserves a hyperbolic plane and I have a smooth curve, or it's really quasi-Fuchsian, then the curve is fractal, has Hausdorff dimension bigger than 1. Here in the higher rank situation, you have new phenomena. So limit sets can be fractal, they can be smooth, but they also can be rectifiable. They can be C1 smooth and nowhere C2. So you have a new world of what are the properties of the limit set. And you still get relations between, interesting relation between looking at the orbit growth in your space and the Hausdorff dimension of the limit set. But now you also have you have more flexibility of looking at orbit growth. So you cannot just look with the Riemannian metric, you can look with orbit growth with respect to also linear forms, and there's a whole new world which is partly explored but not fully yet. So another thing I want to highlight is that we still don't understand the set of all Anosov representations very well. So there's essentially two examples where we understand it. So which is when your Lie group is SF3R, and when your finite degenerated group is either triangle group or the modular group. In this case, we understand fully the set of Anosov representations in SF3R, but in general, it's really difficult to know what happens in the boundary. So you have this nice open subset of the representation variety. We don't know in general how many connected components it has, whether certain connected components can come back at infinity. So there are two pictures by Emily Dumas and Florian Stecker where they try to highlight, and I mean by numerical computation, how this looks like in two of the most basic situations. So here is just one, I mean this is one slide of advertising that there are still many, many, many open questions and directions in which you can go, and also to give you names of several of young people in this area and what they prove. So there are many open questions, starting with topological restrictions. Which hyperbolic groups can admit Anosov representations of a certain type? Extensions to relatively hyperbolic groups, and to getting a generalization of geometric finiteness in higher rank, not just convex co-compactness. There are counting problems. You can look at arithmetic properties, so you can put Anosov representations into arithmetic groups or into lattices, and so there are tons of open questions, and I think also quite a lot of open questions where it would be interesting, I mean like the one I mentioned with cubulated groups admit Anosov representation, to have a bit more interaction with really geometric group theorists and people who come from studying more geometric structures. Okay, so I want to basically end this part on Anosov representation with this picture due to Theo Weissman, which tells you, I mean, the world which seemed very simple for rank 1 Lie groups, discrete subgroups in rank 1 Lie groups, becomes much more complicated in higher rank. So I'm not going to explain the detail. I mean, there's this green part, which I told you a bit about, Anosov representation, and there's this somehow part which extends Anosov representation to somehow the geometrically finite situation, which is already quite complicated and interesting. Okay, so now I want to take the rest of the time and focus on this subclass of Anosov representations, which are formed by what we call higher Teichmüller spaces. So now we forget an arbitrary, we don't take an arbitrary hyperbolic group, we take a very simple group, namely fundamental group of a surface. And we look at representations into a Lie group G, but now we want more than Anosov representations. So Anosov representations give us an open subset of the character representation variety, which contains of discrete and faithful representation. And now we want to find subsets which are not just open, but also closed. So which are really connected components of the representation variety. So where we know we take any sequence going out to, going out to infinity, it stays, any sequence converges to something which is still discrete. And faithful and has the same, and is still Anosov. So I just put this here for people who are interested. I'm not going to use it at all, but once we go and take the fundamental group of the surface, we have many more tools than we had for arbitrary finitely generated group, because there's a correspondence between representation variety with local systems, which we always have, but then with so-called Higgs bundles, which gives us new tools to study this the same object. But I'm not going to use them, so let me just now I want to basically describe to you a bit this higher Teichmüller space, and in particular come to this notion of positivity, which is intimately related to higher Teichmüller space. And for this, I want to recall this. How this looks like for SL2R. So when have a representation of my fundamental group of my surface into PSL2R, so isometry group in the hyperbolic plane, I can characterize or see whether this representation comes from a hyperbolic structure by just looking at infinity. So a representation is the holonomy of a hyperbolic structure on the surface if and only if I can find I don't even need it to be continuous, I wrote continuous here, but if I can find a row equivalent map of the boundary of the surface into RP1, so the boundary of the hyperbolic plane, which preserves positivity in the sense that if you pick a positive triple on the boundary of the surface, which you can identify with S1, and you look at the 3 lines you get in RP1, they are positive as well. So they also are positively oriented. So you can characterize hyperbolic structures in terms of positive maps at infinity. And so when we look at these higher Teichmüller spaces, so you want to find this union of connected components of representation of the fundamental group of a surface into a Lie group G, which consists entirely of discrete and faithful representations. They are actually very closely related to positivity. So there are these 2 examples which I already mentioned to you in the examples of Anosov representation. So the Hitchin component, which I mentioned for SLNR, it exists in a bigger world of where, G is a split Lie group. And the space of maximal representations, which I mentioned for the symplectic group, but which also lives in a bigger world of Lie groups of emission type. In these situations, we know also for about 20 Hitchin component for SL3 for 30 years, and the other for 20 years, we have these connected components consisting entirely of discrete and faithful representations. And what I now want to describe to you a little bit is that these are linked to positivity, and if we think of them in terms of positivity, we actually see there's more higher Teichmüller spaces than these 2. So I want to describe to you what do I mean by positivity if I'm not on the circle, not in RP1, but on a different flag variety. And I illustrate this here for the symplectic group. I want to just focus on this right-hand side where you have maximality. So if you take the symplectic group, it acts on different flag varieties. So it acts on the full flag variety, but it also acts on this space of Lagrangian. And the space of Lagrangian we already saw as appearing somehow in the boundary of the Siegel upper half space. So now, when do I call a triple of Lagrangians positive? So for this, I choose a standard, I can put myself using the symplectic form using the symplectic group in the standard position. So I have my vector space, I have a symplectic basis, E1 to En, F1 to Fn, so that the symplectic form of EIFJ is delta ij, and all the other things are 0. Then I can look, if I look at the third Lagrangian, I can always write it as this upper block diagonal 2 by 2 matrix applied to L minus, where M is a symmetric matrix. And I call the triplet positive if this symmetric matrix is positive definite symmetric. So we just replace reals and positive reals by symmetric matrices and positive definite symmetric matrices. When you want to get a notion of positivity on the full flag variety, it's a bit more complicated. It has to do with total positivity in Lie groups. So you get a unipotent matrix where every minor which you compute and which is allowed to be non-zero is positive. Okay, so you can look at which Lie groups admit some notion of positivity of triples at infinity. And you can actually characterize them, and you see there are these two classes which we know for many years. And then there are two new classes. So there's indefinite orthogonal groups and an exceptional family. And so whenever we have a Lie group in this family, we have a notion of positivity of triplets in a certain flag variety. And once we have that, we can go back to looking at, how did we characterize hyperbolic structures? So we can look at representations which are characterized precisely by this positivity. So you call a representation positive if you find a row equivalent map from the boundary of the surface, which is a circle, so you have positive oriented triplets there, to your flag variety where you have a notion of positivity, so like the one I explained for the space of Lagrangians. And if you find a row equivalent map which maps positive triplets to positive triplets, you call your representation positive. And then this took quite a while for us to finish that. So in some sense, you hope that this gives you higher Teichmüller spaces. So you hope that this gives you an open set and a closed set where every representation is discrete and faithful. And the openness is the easier part. You actually prove it's Anosov. The closeness is the hard part. And to prove the closeness, you actually have to establish, one way to do that is to establish something like a generalization of the Collar lemma from hyperbolic geometry, where we know in a hyperbolic surface, if we have a curve which is very short, then any curve which is transverse to it has to be very long. So now what I want to, I want to now just in the last minute come back to this Markov equation and use this as an example to tell you a bit what I summarized here on this slide, that this notion of positivity gives you a way to systematically understand higher Teichmüller spaces, but it actually gives you a lot of interesting, nice structure and new perspectives on even some classical things. And I want to illustrate this with giving you a somehow matrix version of Markov numbers. So when we look at this space of maximal representations in the symplectic group, right, we have this notion of positivity in the space of Lagrangians, and we somehow saw that the symmetric space, the Siegel upper half space, the symmetric space for the symplectic group is like the upper half space but over matrices. So perhaps it's not so surprising that we can actually parameterize the set of positive representation or maximal representation of the one puncture torus in a very similar way than in the hyperbolic situation. We take this one puncture torus, we pick something like a higher dimensional horse cycle. Now we pick an ideal triangulation, and then we again unfold it, so we have this triangulation, and we associate to each edge of this triangulation, now not a real number, but a real matrix. So you have three matrices A, B, C, and in order for this to really come from a set of coordinates, they have to satisfy this relation that a certain product, which you could think of a certain angle of the piece they cut out of the horse cycle, is actually has to be a symmetric matrix. And then you can define a notion of a flip. So flipping, I mean, you should just flip the edge of the triangle, you compute the new coordinate you get, and you see that it's related by this equation, which, I mean, if things would commute, it's just the same equation you saw for the real numbers. I mean, if you take a 1-by-1 matrix, you have the transpose of a matrix, which doesn't do anything, and so in this setting, you also have an invariant function, so which is invariant by all the flips, which is given by that, which again, if things commute and you have 1-by-1 matrix, it reduces to the matrix, to the Markov equation, classical way. So now you can play the same game. So start with a special solution where you can compute this f and apply all these moves. And you might want, similar to in the Markov situation where we started with 1, 1, 1, so integers and things where this product is positive, you might want to add some positivity or integrality condition. So, and you can start playing with it. So even if you start with very simple examples, so for example, ABC, where you take A to be the identity matrix, B to be this upper triangular matrix, and C to be its inverse, then when you compute, you get this family of matrices. When you compute their trace or determinant, you actually get polynomials in T, which are integral, give you integers for every integer T. And if you specify them at T equals 0, you come back, you get back the classical Markov numbers. So you can think of this as a one-dimensional deformation of Markov numbers. You can play more with it, so you don't necessarily need to do matrices. What you really need is a ring with involution, and play with complex numbers. So this is in some sense even easier than Markov numbers. So you get new complex Markov numbers where the norms of your complex number just behave like a real Markov number, but the arguments also change, and there are a lot of interesting questions about what can you say about the arguments, depending on your initial configuration of complex numbers. And another thing which I would like to advertise as something to explore is you can also take group rings, and with the involution given by G going to G inverse. And for finite groups, it's something which is really, I mean, you can make sense of positivity and some of the integrality properties you want. For infinite groups, it's, I think, even more interesting and but also more difficult. If you play with this with finite groups, you get, in some sense, deformations of Markov numbers in the group ring, which if you specify them at the generator of your group, so for example, if you take a cyclic group, you get back classical Markov numbers. And with this, I want to stop and just bring back some of the pictures, and I hope I could show you a little bit that there's a nice, beautiful world beyond hyperbolic geometry when we go to non-positive curvature. There are many things yet to explore. Thanks.
Thank you, Anna. Do you have questions or comments?
Just a short question, probably a stupid one, but all the Anosov representation and all these, there are the risky dense in the group, that's clear?
No. But there are Zariski dense ones.
Always, you can get always also Zariski dense?
Well, you can, I mean, in many, so for surface groups, for example, you know that, I mean, Zariski dense representations are dense,
But
so you
say
can.
for, if you take triangle groups, do you have enough?
For
Which is a finite extension of surface group?
Yes.
Do you have enough representation? You said you take any hyperbolic, not necessarily torsion-free, right?
No, it doesn't have to be torsion free. I mean, you could take triangle groups,
Yeah,
but in general, it's not. I mean, okay. I mean, for an arbitrary group, I cannot say something like. I mean, if you take this arbitrary group, you embed it, it's definitely going to be deformable to a Zariski dense one, right?
no, that's clear.
But-
But like you started, the first example was that you start with say the pi1 of surface inside.
Yes.
SL2, you embed irreducibly SL2
Yes.
to SLNR, and then you take deformation.
Yes,
Right?
and then they are.
For the surface group, I understand.
Yeah.
But for the triangle groups, we
For
can
triangle groups, there are also many examples where we know that we can deform, and we can deform to Zariski dense ones. I mean, this is so. but of course there are situations where, I mean, you might have obstruction to deforming to something Zariski dense one. So I cannot give you a general statement. But the nice thing now, what you can use, and this is actually, so I mean, you can play with it because you can, I mean, you embed your group in some G. So you can take any linear representation of G, and and eventually, in many cases, eventually you can deform, right?
That's some interesting application to the theory of finite simple groups from consideration like that. I will tell you after that.
No, but there is an example given in Rick Schwartz's talk about the paposphere, where he described essentially the deformation of the modular group, which is a triangle group inside SFER. And
yeah, but I mean, this is the case where, I mean, even
Zariski dense.
no, there you have Zariski dense things. I mean, there's also this, when you really take, I mean, the triangle group by Levy and Stecker, where you can describe, I mean, you have Zariski dense ones, you can describe explicitly what the set of Anosov group is.
I have a question. Yeah. So the Markov equation describes also the SL2C character, right? The ones with torus. So in your generalization to SP2N or SP4, you have sort of the same kind of equation describing that component or the whole character, right?
To some extent, yes. I mean, there's a few, what you had here, if you do this kind of coordinates, you don't need the reals. I mean, I can do it over the complex as well. And similar to the SL2C, I mean, there are certain things, I need some transversality. I mean, it's a decorated character variety because I have to choose this kind of horse cycle.
Yeah, okay.
And I need, in some sense, transversality conditions. I describe a Zariski open subset, right? Because I need, because I want these matrices to be invertible actually, and so for this I need that if I look at basically the flags, the Lagrangians I associate to two endpoints along a line of my triangulation, that they have to be in general position.
Here it looks like you have flips and moves that leave invariant an equation which you have not written down. That's what I mean.
No, they leave invariant this equation.
FABC.
Okay. This is the equation with, I mean, and this has to do with, in some sense, the decoration. I mean, it's the same as, I mean, you cannot change the length of this horse cycle you picked, which, I mean, this is the thing they leave in there.
You have more questions? Well, let's thank Anna again.